Application of recursion. And what it says, if you can solve n minus 1 cases, then easily you can solve the nth case. Okay, that is the main, we can say, the motto of your Tower of Hanoi. Okay, if we consider this diagram, so here three poles are there, A, B, C. In A pole, here rings are mounted. Okay, three rings we are going to consider. Okay, three rings are mounted. Now what we have to do, from this A ring, we have pole A. From this pole A, we have to move all these rings to this pole C. Okay, and we have to maintain the same order, means the largest one at the bottom side, second largest at the middle side, and the smallest one at the topper side. Okay, so smaller disk must always come before the larger disk. This hierarchy we have to maintain. Okay, so how we can do it? Can any one of you explain it? Okay, this is another pole. We can use this B pole for the help. Getting what I am saying? What you have to do, consider here, whenever I am moving this disc or ring to the another pole, then your smaller disc must always be above to the larger disc. Okay, suppose I move B here. Okay, if I move B here, or if I directly move this smaller disc to this C, and then if I again move this second larger disk to on this C, but what happens here? The smaller disk will come at the downside and larger disk will come on the upper side, but that I don't want. So what should be the solution? Can any one of you give me the solution? This is the in general problem. Am I audible to everyone?
Yes,
Yes,
ma'am.
ma'am.
Ma'am, we will move the disk from A to B, then B to C.
Means first disk we will move from A to B and then from B to C. Then what
No,
is the
ma'am.
use?
After putting all disk from A to B, then B to C.
First we have to keep the disk, all disks to this B. Is it like that?
Yes, ma'am.
But see here, what we want, smaller disk must always come above the larger disk. We cannot keep larger disk on the smaller disk. Getting my problem statement? लक्ष आहे सगळ्यांचं?
Yes, ma'am. Yes, ma'am. Ma'am, by putting the smaller disc in the C and then by middle disc in the B and again the largest disc in the C.
Okay, we will see. Okay, so how to do that? We will see here. Okay, first, see, we will be using this. We will be doing this using a spare pole, that is your pole B. Okay, in our case, A is the source pole and C is the destination pole. And we can call this B as the spare pole. Okay, to transfer all the rings from A to C, we will first shift the upper two rings, that is n minus 1 rings, from source to the spare pole. Okay, how to do that? See how it exactly is. And one more thing is there, we have to move only one disc at a time or one ring at a time we can move. We cannot move two rings at a time. Okay, this is also the constraint. So what we have to do, we move the first two rings from pole A to B as shown here, and then we move. Once this scenario comes, then what we are going to do, we are going to move this larger disk from A to C. Okay, so how we are going to do it, we will see step by step. Okay, here one diagram is missing, I will tell you. See, these 3 poles are there. कोणत्या डिपार्टमेंटचे? कम्प्युटरला कोणी नाहीये वाडेकर. IT डिपार्टमेंटला विचाराल एकदा. Okay, so what we will do, we are going to move this smaller disk first to this C. Okay, this disk we are going to move here. Then this second, I will call it as 1, 2, and 3. Okay, then I will move this second disk here. Okay, then here, which disk is remaining here? Disk number 3 will remain here. So after that, what I will do? This is my first step, or A step I will call. This is my A step, this is my B step. Okay, now what will be my C step? Again, I will move this A or disk 1 on this disk 2. Sorry, pole B, I can say. So this is your step number 3, C. Okay, so now this will remain empty, and then I can move this on the pole C. Getting everyone? This will be my third disk, like this. I'm going to move. Okay, so once I will do this one, okay, scenario is like this. Then I will move this to your pole C. Okay, then once I move this to the pole C, then I can move this step to this upper one to this pole A, and then I can move this to this pole B, and then from A to C it will come. So we will see here how we are going to move it. Okay, I will consider, see, we have considered this as pole 1, 2, disk 1, 2, 3, and poles are A, B, C. So what I will do, I will write here from A, pole A, I will transfer the disk 1 to where? To this C, pole C. Getting everyone?
Yes, ma'am.
Okay,
Yes,
so
ma'am.
these 2 poles three poles I am going to consider. A, B, and C. These 3 poles are there. Okay, from A to C it comes. So here is pole number 1. Then what I am going to do? 2, I am going to move from A. I am going to move the disk 2 to this pole B. So currently here pole number 2 is there. Disk number 2 is there. Understood?
Yes, ma'am.
Okay. Now from this pole C, on pole C, this one disk is there. So I'm going to write down which disks are present on currently on pole, each pole. Okay, so now B will contain the pole number, disk number 2. Now from pole C, I'm going to remove the disk 1, means from C, I'm going to remove disk 1, and which I'm going to put it on the disk B. So now disk B contains 1, 2, and above on that it has the disk number 1. It has now 2, 1. Getting everyone?
Yes,
Yes,
ma'am.
ma'am.
Now what your pole C contains? Which disk your pole C contains?
Nothing, ma'am.
Nothing. Okay, your pole C does not contain any disk. But what your pole A contain? Disk 3. Okay, it contains the disk 3. So what we can do? This is the largest disk, so we can move that to the pole C. So how we are going to move? From A, move disk 3 to where? To C. So now what your C contains is the 3. So I'm going to write down here 3. 1 is not there, so here 3 is there. Understood everyone? Now
Yes, ma'am.
what your A contains?
Nothing.
Nothing. Okay, A contains nothing. So what we can do? See, directly I cannot move this 1 on 3. Okay, because again 2 is remaining. So I cannot place disk number 2 on disk number 1. What should be the sequence? Your smaller disk must, this statement, smaller disk must always come above the larger disk. So I cannot move from this to C directly. So instead of that, what I needed from this B, I need to move. Where I am going to move? From disk B, which from pole B, which disk I am going to move? Disk number 1. And where I am going to move it? On this A pole, we are going to move it. So what your A contains is the disk number 1. So currently your disk number 1 contains, disk number A contains 1. Understood, everyone?
Yes, ma'am.
Yes, ma'am.
Okay, so this contain A. So this one has been removed from this B. Okay, now what should be the step? This is like a playing a game. Okay, so what should be the next step? Any one of you? Which disk I need to move?
Ma'am,
One,
2.
two, or 3? Yes,
Second disk.
2 I needed to move to this pole C. Okay, so from pole B, I'm going to move disk 2, and where I'm going to move it? On disk C, yeah, sorry, on pole C. And now what your pole C contains? Already it has 3, and then now it contains 2. So on this 3, there is one another disk called as 2. Getting everyone? Now
Yes, ma'am.
here pole B is pole B is empty, we can say. Now one is there on this pole A, so we can directly move this disk one from pole A to pole C. So how I'm going to write down A, one we are going to move, and it will come on this C, and disks are 3, 2, and 1. Understood, everyone?
Yes, ma'am.
Okay, so next scenario will be like this. Understood?
Yes, ma'am.
Okay, can you write down these steps? Understood this one? You can write like, you can draw like this. Somewhere in your terms, you can write down. You can draw this tower of Hanoi. Done?
Done, ma'am.
Done. Just give me 1 minute. Huh? There is error in the program. Let me check. Oh, yeah. Move, move. In destination spare no percent C. Source destination. Implicit declaration of function module. Line number 15. Three, comma, 8. B. Here we are going to see when best case will occur. Okay, best case will occur if n is equals to 1. Okay, then n means number of rings, we can say. If number of rings are 3, number of rings are 1, then we can directly move from ring A to C, and we uses only the B as pair. So we can say that this is the best case. Okay, and recursive case, when recursive cases will happen, move n1 rings from A to B using C as pair, move the one ring left on the A to C using B as a pair, and then move n minus 1 rings from B to C using A as pair. So we can, so these two cases may get in Tower of Hanoi. Here, what we are doing, just give me 1 minute. Have you written this program? Am I audible?
Yes, ma'am.
Have you written this program?
Yes, ma'am.
Okay. So here we are calling this function move function, I think it is predefined function, so you can change this name. Move n comma a comma cb, acb. These are the pole names. This is the source pole name. This is the destination pole name, and this is the spare pole we are using here. Okay, and n is number of rings. So here in this case we have used 3 rings. So you can specify accordingly. Then what we are going to just display here, from where to where we are moving, means like here we have written no like this. Okay, so this is this kind of your output is from A to C, from A to B, then C to B, A to C, B to A, B to C, and then mm, A to C. Okay, these type of steps we are going to write down here. Okay, move from which pole to which pole, only that we are going to just write down here. Okay, then, and here we are calling the recursion program. If n is equals to 1, simply we are writing from source to destination we are specifying here. Else what we are doing, we are calling here the recursion function. Move n minus 1, source, spare, and destination. So your spare will work as the destination here, and destination will work as spare. Okay, then move 1 comma source comma destination, source destination spare, and then move n minus 1 spare destination source. So you can take n value and you can do this calculation. Okay, this program will happen like this. Okay, two move disk you are moving here, then one here, then again you are moving this n minus 1 disk over here. Like this it will work out. Okay, then if we consider one ring, if there is only one ring, then simply what we are doing, from this source we are moving to the destination. If we have two rings, then what we are doing here, from source we are moving to the here, from source we are moving it to the spare pole, and then from source to destination we are moving, and from then spare to destination we are moving. And another one is same, just we have seen. Okay, 3 poles are there, then smaller one we move to the destination, then second larger we move to the from source to spare, then again from destination to the spare we have moved like this. This steps, 8 steps will get followed. Okay, so these two are the scenarios we can see. So here we have finished the Tower of Hanoi. Then next we are going to see recursion versus iteration. So we can say that recursion is more of a top-down approach to problem solving, in which original problem is divided into smaller sub-problems. Whereas in iteration, this iteration follows up the bottom-up approach that begins with what is known and then constructing the solution step by step. And recursion is an excellent way of solving complex problems, especially when the problem can be defined in recursive terms. Okay, and for such terms, a recursive code can be written and modified in a much simpler and clearer manner. The next one, we can say that recursive solutions are not always the best solutions. In some cases, recursive programs may require substantial amount of runtime overhead. Okay, it may take the more time, and we can say that it becomes the more complex if you use sometimes it becomes more complex if you use this recursion. Okay, therefore we in implementing a recursive solution, there is a trade-off involved between the time spent in constructing and maintaining the program and the cost incurred in running time and memory space required for execution of the program. Okay, here when recursive function is called, some amount of overhead in the form of runtime stack is always involved. Then that is before jumping to the function with a smaller parameter, the original parameters, local variables, and return address of the calling function are all stored on the system stack. We all are familiar that whenever we are calling any recursive function, the function who is calling the function, all its parameters, these parameters we store, all the parameters, variables and addresses of the calling function we store on the stack. Okay, therefore while using the recursion, a lot of time is needed to first push all the information on the stack, and when the function is called, and then again in retrieving the information, means once that called function has been executed, and when it returns to the calling function, then again to restore that information, again it takes the time. Okay, so what we conclude here, one must use recursion only to find solution to a problem for which no obvious iteration solution is known. Okay, and which are the different advantages of recursion? Here, recursive solutions often tend to be shorter and simpler than non-recursive ones. Code is clear and easier to use. Recursion works similar to the original formula to solve a problem. And recursion follows a divide and conquer technique that we have seen in Unit 2. Divide and conquer technique to solve the problems, and in some instances, recursion may be more efficient. Okay, only in limited instances we can say. And which are the drawbacks of recursion? Here, for some programmers and readers, recursion is a difficult concept, and recursion is implemented using system stack. And if the stack space on the system is limited, recursion to a deeper level will be difficult to implement. Then aborting a recursive program in a midterm can be a very slow process. Using a recursive function takes more memory and time to execute as compared to the non-recursive counterpart. As here we have said that every time we needed to push it on the stack, and whenever we come back we need to pop it from the stack. Of course it takes the more memory and the time to execute, and it is difficult to find bugs, particularly while using global variables. And the advantages of recursion pay off for the extra overhead involved in terms of time and space required, we can say. Okay, so this is all about recursion. Okay, now next we are going to see, I think yesterday we have seen it, no? Inserting a node after a given node in the linked list program. Have we seen it? Am I audible?
Yes, ma'am.
Yes, ma'am.
Ma'am, deletion from position.
Yes, for deletion we are going to see deleting a node from a linked list. Okay, so three cases we are familiar. First node is deleted, last node is deleted, and the node after a given node is deleted. Okay, so before that we have seen how to delete from the start and first node, how to delete last node, and before that again we will see one more condition, underflow condition. Here I think in insertion overflow condition also we need to consider. So underflow condition, okay, when we try to delete a node from a linked list that is already empty, then we call it as the underflow. Okay, so when your start is equals to null, we can, if we want to delete the more nodes, then we can say underflow condition has been occurred. Okay, when we delete a node from a linked list, we actually have to free the memory occupied by the node. So whenever we delete node, then you must need to free that memory. Okay, and the memory is written to a free pool, that is we have seen avail something. Okay, so it will be written to this avail one. Okay, so it can be used by, so that it can be used to store the other programs and data. Whenever, whatever be the case of deletion, we always change the avail pointer so that it points to the address that has been recently vacated. Okay, so this is about the underflow condition. Now we have seen this example, deleting the first node from a linked list. Okay, what we are doing here, if this is the scenario and if you want to delete the first node, here start is there, so what we are assigning here, start is equals to start of next. Here this is your start of next, so you are pointing start of next here, so here start comes. Understood everyone?
Yes, ma'am.
Okay, so we will say algorithm. If start equals to null, write underflow, go to step 5, that is exit. Else set ptr is equals to start. Okay, one temporary pointer we are taking, ptr is equals to start and start is equals to start of next, and free ptr means whatever space has been occupied by this node, we are going to release that one, free ptr. Understood?
Yes,
Yes,
ma'am.
ma'am.
Okay, write down this algorithm. Have you drawn this diagram?
No, ma'am.
Draw this one. Sharma sir. Done? Okay. Write down this algorithm. Done?
Done, ma'am.
Is 67 present today? Okay. सी तुमच्या क्लासमध्ये ना मेसेजेस कसं करतात तुम्ही, जसं तुमच्या फ्रेंडला मेसेजेस करता ना, त्या पद्धतीने तुम्ही मेसेजेस करता. मला एक शेअर करायचंच आहे, तुमचा क्लासमधला कोण आहे तो? 67. लेट मी स्टार्ट माय व्हॉट्सअप पेज. तुमची पद्धत बघा मॅडमना बोलायची. We are checking here if start equals to null. Okay, that complete has been explained here. Code we are going to see. First, deleting node for the beginning. This method we are, function we are going to write down, delete beginning. That start we are passing here. Then struct node PTR, one temporary pointer we have taken, structure pointer we have taken. Then PTR is equals to start. That is what we have done. PTR is equals to start. So we have done PTR is equals to start. Start is equals to start of next. And pre PTR return start. So this is the code for your function. Okay, write down this code. Or anyone going to share the PPT, you can write down at that time. The next one is the deleting the last node. We have seen this also, no? Deleting the last node. Have we seen it? Yes, no.
Yes, ma'am.
So deleting means what we are doing? Next of next, I think we have checked. We are starting from the first node. Then we are checking the next of next. If next of next is null, then we are deleting that one, or we are just making the one node before next pointer as null, and we are freeing this space. Okay, so what we are doing here, if start equals to null, then we are writing underflow, then go to step 8, exit, then set PTR is equals to start. We are traversing from this start, and then repeat step 2 and 4 while PTR of next is not null. Okay, we are going to repeat till PTR of next is not null. Set pre PTR is equals to PTR. One pre PTR we are taking here. So 3 pointers are here currently. Start, pre PTR and PTR. 3 pointers are there. Then set PTR is equals to PTR of next. Currently here it is. Then what we are doing, if PTR of next is not equals to null, then PTR of next, PTR is equals to PTR of next. So currently your PTR will point here. Then again go here, PTR of next, whether PTR of next is null, no, PTR of next is not null, then what, pre PTR is equals to PTR, so PTR, and this is also pre PTR. Okay, and next is, to this pre PTR I will mark as, see currently it is PTR of next is not null. So what we are doing here, PTR is equals to PTR of next. So your P will point here to this pre PTR. I will write it as R. Okay, then next is pre PTR is equals to PTR. So here pre PTR is equals to PTR and PTR is equals to PTR of next. So here currently your R is pointing here and P was pointing here. Okay, then PTR is equals to PTR of next. So your P will point here. Now whether PTR of next is null? No. So if it is not null, then pre-PTR is equals to PTR. So currently now your R will point here, and next is PTR of next is equals to PTR is equals to PTR of next. So your P will point here. Again, P of next is, PTR of next is not null. So what? R pre-PTR is equals to PTR. So here your pre-PTR will point and PTR is equals to PTR of next. So here your P will point. So in this way traversing will get happen. Okay. Now when we will see PTR of next is equals to null. Let us assume your PTR is pointing here. When your PTR is pointing here, then your pre-PTR will point here. Now, when this condition is false, then what happens? Pre-PTR of next is equals to null. You are putting, so here pre-PTR is there. Sorry, pre-PTR will pointing here. You are marking it as null, and then free PTR. So whatever space has been occupied by this node, you are going to just release that space. So after that, here is your pre-PTR and you are releasing this one. So start, then 173426, 173426, and you have marked it as the null. So in this way, this algorithm will work out. Understood, everyone?
Yes, ma'am.
Okay. So same we have converted into the program. Delete end node, start node we have passed here. Then struct node PTR and pre-PTR. PTR is equals to start. Then while same condition, while PTR of next is not null, then what pre-PTR is equals to PTR and PTR is equals to PTR of next, and then pre-PTR of next is equals to null and free that PTR. So this is the code for deleting the last node from the linked list. Okay, here this condition, deleting the node after a given node in a linked list. Okay, suppose we have to delete the node that succeeds the node which contains data value 4. Okay, here if we want to delete this 4, we are going to assume. Okay, so what changes we are going to do here? So first start is there and last node contains the null pointer. So take pointer variable ptr and pre-ptr which initially points to start. So your start here, start has been pointed. So start, pre-ptr and pre-ptr. These 3 pointers we are assigning here. Now move pre-ptr and ptr such that pre-ptr points to the node containing val. Val means the value, which node, value of or the data part of the node whose node you want to delete. So currently val means 4 we can consider. Okay. So move pre-PTR and PTR such that pre-PTR points to the node containing val and PTR points to the succeeding node. So how we are going to move? This pre-PTR will point to the node which you want to delete and PTR will point to the succeeding node. Getting understood?
Yes, ma'am.
फक्त एक जणच आन्सर देणार आहे. समजतंय का सगळ्यांना? 55.
Yes, ma'am.
46.
Yes, ma'am.
41.
Yes, ma'am.
समजतंय ना? 27. 23.
Yes, ma'am.
Okay. So we are going to move your pre-PTR and PTR in this way. So what your pre-PTR contains? Where your pre-PTR will point? To the node which we want to delete, and the PTR will point to the, means after traversing, and PTR will point to the next node, succeeding node we can say. Okay, so here start is there. So in the same way we are going to write down C. If start equals to null, we are going to write down underflow. Then set PTR is equals to start, set pre-PTR is equals to PTR. So here your 3 pointers are pointing. Then repeat step 5 and 6, these steps, while pre-PTR of data is not equals to null. This condition is important. Getting num is the value part which we want to delete. We want to delete 4, this node whose data is 4. So we are providing here num with that value. Getting?
Ma'am, I guess we have to delete 2.
Yes, ma'am. The succeeding node after
Yes,
the
ma'am.
data.
The node
mean
which
value.
succeeds 4.
Yes, ma'am. The value we have taken 4, so the node which succeeds the value node.
Okay, we will check. Once algorithm runs, then we will check. Okay?
Okay,
Which
ma'am.
node will get deleted. We are going to write down stepwise here. Now see here. Then repeat step 5 and 6 while pre-PTR of data is not equals to null. In this case, where your 3 pointers are here, we are assuming that value is equals to 4. Getting? Value, or we can say num. Num is equals to 4 we are going to consider. Now set pre-PTR is equals to PTR, and means same here, your pre-PTR is pointing here itself, and PTR is equals to PTR of next. So where your PTR will point now? To this 7? Yes, no?
Yes.
Yes, ma'am.
Okay. Here your PTR is pointing, and here your pre-PTR is pointing. Okay. Next is repeat this one. Again, now pre-PTR of data is not equals to num. Okay. If pre-PTR of num data is equals to num for no. Okay. Then what? Pre-PTR is equals to PTR. So here your PTR is pointing. So here your pre-PTR will come. This reference will go, and then PTR is equals to PTR of next. So here your PTR of next is pointing. So here your P will come. Getting?
Yes.
Yes, ma'am.
Yes, ma'am.
Okay. Now next, again go to this condition. Pre-PTR of data is not equals to num. Yes, condition is true. If condition is true, then what? Pre-PTR is equals to PTR. So here your PTR is pointing. So R will come here, and PTR is equals to PTR of next. So here your P will come. Understood?
Yes, ma'am.
Again check whether pre-PTR of data is equals to num. Yes, no.
No, ma'am.
No.
No. Okay. No. So what has to do? Pre-PTR is equals to PTR. So this will become your pre-PTR. Getting? And PTR is equals to PTR of next. So here it is PTR. P is pointing. Now pre-PTR of data is equals to num. Whether this condition is true?
Yes, ma'am.
Okay, if this condition is true, then here end of loop will happen, and then set temp is equals to PTR. So here P is there, we are assigning here temp is equals to PTR. We will see which node will get deleted. Okay, 2 will get deleted. Set PTR of
Yes, ma'am.
next, set PTR of next is equals to, oh, sorry, pre-PTR of next is equals to, this is pre-PTR of next is equals to PTR of next. We want to delete the node that succeeds the node which contains the value 4. Okay, which succeeds the node, that succeeds the node. Then set pre-PTR of next is equals to PTR of next and pre-temp. So we are temp is pointing here. So we are releasing this one. So this will get deleted. Your linked list will be like this one, pre-PTR. After a given node. So sorry. So 4 after a given and before a given, like that is the concept. So we have given the value 4. So we are going to delete the node after the given node. Okay, so 2 will get deleted and you will get the output as 1, 7, 3, 4, 6 and 5. So 2 will get deleted over here. Understood?
Yes, ma'am.
Okay. Then will you write down this algorithm?
Yes, ma'am.
Done. Done.
Yes, ma'am.
Yes.
Okay, we will see program segment. Okay, structure node, pointer delete after, struct node, pointer start. Start we are passing here, then two pointers we are taking, pointer PTR, pre-PTR, then int value. Okay, we are taking that value after that node, after that given node, we are deleting the node. Okay. Then enter the value after which the node has to be deleted. We are reading that value. Then PTR is equals to start. Pre-PTR is equals to PTR. Same algorithm we are converting into the problem statement. Here while is there. So while pre-PTR of data is not equals to val. Okay, write down this program segment. कशात आलेलं? ते झाडे मॅडमचं माझं कालच दिलंय तुम्ही. एवढ्या लवकर कसं काय येत आहे? पहिले येत नव्हतं.
मला ती एक वर्षाने आली पण
हो ना,
आता पटापट येते बघा. दिवस लावतो.
तेच म्हणे.
इंजेक्शन चांगलं होते.
आता माझं आणखीन एक येईल, मी आजच दिली.
चालते का?
Done? Understood everyone?
Yes, ma'am.
Okay. Then we are going to see sorting the list. Okay. So 2 pointers. What we have to do to sort the data? We are considering the ascending order. Okay. Pointer. Okay. We are going to consider this data. Suppose 3 nodes we will consider. Okay. 10, 5, 10, 15, and suppose 12. Just assume this data. Okay. We are going to consider this one. Here, start will be, of course, start pointer will be here. Then PTR1, 2 pointers we are taking, PTR1 and PTR2. PTR1 is equals to start. So I am going to consider this as the P1. Then while PTR1 of next is not null, condition is true, its next part is not null. Then PTR2 is equals to PTR of next, PTR1 of next. So your PTR2 will point here. Getting everyone?
Yes, ma'am.
Okay. Now, why PTR2 is not equals to null? Whether this condition is true, PTR2 is not null,
Yes, ma'am.
PTR2 PTR2 next is not null, or PTR2 is not null. So we are going to check if PTR1 or PTR1 data is greater than PTR2 data. Okay, P1 data and P2 data, whether this condition is true or false? False. Okay, so what it will do? It will come here. PTR2 is equals to PTR of next. So here your P2 will point P2. Now next curly bracket, this is the end of while. Okay, I will write here. I will do. Now is it clear? Can you get the problem statement? Now this is the if part. If this condition is false, we are running this one. PTR2 is equals to PTR2 of next. So your P2 will point here. Now this is the closing bracket. Closing bracket means loop. Loop means again it will check whether PTR2 is not null. Whether PTR2 is null? No, PTR2 is pointing somewhere here. So it will check PTR1 of data, that is 12. Okay, P1 is pointing here. So P1 greater than P2. Yes, no? Condition is true or false?
True.
Condition is true. So what we are doing? Temp is equals to PTR of data. Means your T is equals to the PTR1 of data. Means P1 is equals to 12. Then PTR1 of data is equals to PTR2 of data. Means here we are moving here 10, and then what? PTR2 is of data is equals to temp, means here 12 will come. Getting 10, 50, 12. Understood?
Yes, ma'am.
Okay. Now PTR2 is equals to PTR of next. Means now this is null part. So what your P2 will contain now? It is equals to now null. P2 is equals to null. Now check here, it will go here, PTR2 is not null. Now this condition is false. Yes, no? If this condition is false, it will come out of this loop, and here what we are doing, PTR1 is equals to PTR1 of next. So now your P1 will point here. So now your P1, PTR1 will point here. Getting? Yes, no?
Yes, ma'am.
Okay. Now PTR2, now PTR of next is not null. Whether this closing bracket means again it will come here. Now PTR1 of next is not null. This condition is true, so it will come here. PTR2 is equals to PTR1 of next. So your PTR2 will point here itself. Now while PTR2 is not null, your PTR2 is pointing to this part, so we can say that this condition is true. So if PTR1 of data is greater than PTR2 of data. Condition is true. So again do swapping. So here 12 will come and here 15 will come. Okay, then PTR2 is equals to PTR2 of next. PTR2 is pointing here. So its next is null. So your PTR2 is equals to what? It is null. Okay, fine. So it will not go into this loop. This condition is false. It will come here. PTR1 is equals to PTR1 of next. So here your P1 will point now. Okay. Then this closing bracket means here it will come. It will check PTR1 of next is not equals to null. PTR1 of next is equals to null. So this condition is false. It will come to this return statement, return start. So it will return start means now this the list is sorted one 10, 12 and 15. Understood?
Yes, ma'am.
Okay, this is the sorting of your linked list. So will you write down this code? Everyone understood this? Yes, no?
Yes, ma'am.
कोणाला समजलं नसेल तर प्लीज विचारा. चालेल, हे लिहा. मी 2 मिनिटात जॉईन करेन. चालूच असू दे, तुम्ही लिहून घ्या. किंवा तुम्हाला एक 5 मिनिटाचा ब्रेक हवाय?
Yes, ma'am. Yes, ma'am.
ओके, चालेल. 4:35 ला सगळेजण जॉईन करू. मी 4:35 ला आपलं स्टार्ट करेन. ठीक आहे, टेक अ 5 मिनिट्स ब्रेक. लॉग आउट करून ट्रेड लिस्ट, circular link list we have seen. We will see only insertion in the circular link list and insertion into the doubly linked list. So can you be able to write down algorithm and program for deletion from the deleting a node from the circular link list and deleting node from the doubly linked list? Yes, no?
Yes, ma'am.
Okay, only we are going to see inserting a new node in a circular linked list. Okay, so 2 cases are there when we want to insert a linked list. So the new node is inserted at the beginning of the circular linked list and is inserted at the end of the circular linked list. So we are going to consider here. See. Consider this linked list 1734267. This is the data. Your last node is pointing to the first node. Okay, so it becomes the circular linked list. Now we consider this new node. Okay, so allocate memory for the new node and its data part to the 9. So we have assigned here. Now take a pointer variable. Take a pointer variable PTR that points to the start node of the list. So here PTR will point. Now move PTR so that it now points to the last node of the list. So you need to traverse this list. Your PTR will traverse through this list and now PTR comes here. Okay. Now add the new node in between PTR and start. So here PTR is there. New node is there. This is the start node is there. So what you are doing here, your PTR of next will point to this new node and new node next will point to the start and now next is you are making the start as the new node. Getting everyone?
Yes, ma'am.
Okay,
Yes,
so
ma'am.
this is inserting a new node at the beginning of the circular linked list. So we will see algorithm here. See, if avail equals to null, then write overflow. If there is no available space, we are going to write down this one. Else what we are going to do? Set new node is equals to avail and set avail is equals to avail next. Now set new node of data is equals to value. Here we are creating the space for this new node, we can say. Now we are assigning value to this new node, means we are assigning 9 to this data part. Then here set ptr is equals to start. Set ptr is equals to start. Now start and ptr will point to the same node. Then repeat step 7. This step we are going to repeat till start of ptr of next is not equals to start, means we are going to traverse. Currently your start is pointing, ptr is pointing here. Ptr of next is equals to start? Yes, no? Tell me whether ptr of next is equals to start. Yes, it is true or false?
False, ma'am.
It is false. So what we have to do next? ptr is equals to ptr of next. So here ptr will point here. Okay, we are going to repeat these steps. We are going to iterate this step. Okay, again ptr of next is equals to start, condition is false. So your p will point here. Again its next is not pointing to start. So your p will now point here. In the same way it will come here. Now, okay, here let us assume your ptr is here. Now ptr of next is equals to start. Is this true?
No, ma'am.
No. So your p will point here. Ptr is equals to ptr of next. Now ptr of next is equals to start. It is true or false?
True.
True. So it will come out of this loop. Okay. It will end of loop and then set new node of next is equals to start. Okay. So new node. This is the new node. Okay. New node of next is equals to start. So we are assigning this one. Getting?
Yes, ma'am.
Okay. Next is set ptr of next is equals to new node. Here your p is pointing. So p is here. So its ptr of next is equals to new node. So your ptr will point here now. Ptr of next will point to this new node. And then set start is equals to new node. So your now start will point to this new node. Getting? Understood?
Yes, ma'am.
Okay, so this is about inserting a node at the beginning of a circular linked list. Now next is this is the program statement. Same things are there. Okay, we are taking here 2 pointers, new node and ptr. Start we are passing here. Then int num value we are going to read. Then new node, we are allocating space for the new node. Data is equals to num. And then ptr of start, ptr is equals to start. And then we are traversing this ptr till the last node. And once this last node comes, then what we are doing? ptr of next is equals to new node of next is equals to start, and start is equals to new node, and we are returning the start. Understood? Simplest one. Yes, no?
Yes, ma'am.
Okay. Then next is inserting node at the end of the circular linked list. So where we want to insert, same, we are allocating space for the memory for the new node and initialize its data part to 9. Then we are taking ptr here. Now same, we are move the ptr so that it now points to the last node of the list. So here your ptr is pointing. Now add the new node after the node pointed by ptr. Here your ptr is pointing, so we are adding here the new node, and we are assigning ptr of next is equals to ptr of next to this new node, and new node of next is equals to start. We are going to do like that. Getting? After this, add the new node after the node pointed by the PTR. Getting?
Yes, ma'am.
Next one. Okay, we'll see algorithm here. See, if avail equals to null, write overflow. Here we are assigning the memory location to the new node. New node of data is equals to val. And then what we are setting here? New node of next. Initially itself we are making. New node of next is equals to start, that we are assigning here. Okay, then set PTR is equals to start. Then repeat while PTR of next is not equals to start. Then set PTR is equals to PTR of next, and PTR of next is equals to new node. After this one, we are going to assign this. So inserting node at the end of the circular linked list, deleting the node. So two cases are there. First node is to be deleted and the last node is to be deleted. From this algorithm, you will be able to understand it. Okay. Then we will see doubly linked list. We have seen this one. So we will see how to create. Have we seen this? I think we have seen this one, no? Linked list. Creating doubly linked list we have seen. Now inserting a new node in the doubly linked list. So four cases are there. New node is to be inserted at the beginning, inserted at the end. Then new node is inserted after a given node and inserted before a given node. So these four cases are there. We'll see only two cases. Rest of the part you can check. Okay. Inserting node at the beginning. So whenever we are inserting node at the beginning, first what we need to do, we need to create a node. Okay, this is the first node. This is the list. Consider first node, previous pointer is null. 1 start pointer is pointing to this node 1 7 3 4 2, and last part next pointer will be null. Now this is the node. Allocate memory for the new node and initialize its data part to 9 and previous field to null. Understood this part?
Yes, ma'am.
Now add the new node before the start node. Now the new node becomes the first node of the list. So what we needed to do here, this is the new node. So what we are assigning here, new node of next is equals to start. Getting? New node of next is equals to start, and start of previous is equals to new node that we are going to assign. Okay, these two pointers. So you are going to insert it at the beginning. We'll see algorithm here. See, set new node is equals to avail is equals to avail of next, new node of data is equals to value, and new node of previous, this we are going to mark. New node of previous is equals to null, that we have marked here. Then new node of next is equals to start. New node of next is equals to start. That is what we done here. And then set start of previous is equals to new node. Start of previous is equals to new node, and then set start is equals to new node, and we are marking it as the start. Simplest one. Understood?
Yes, ma'am.
Too simple it is. Okay, compared to single linked list, your doubly linked list is quite easier if you understand the concept, then only. Otherwise it is much tedious. Okay, this is about inserting node at the beginning. Then this is the code. Same algorithm has been converted into the code. Then inserting a node at the end of the doubly linked list. So what changes we need to do here? काय करायला लागेल आपल्याला?
Ma'am, previous pointer we have to link.
Previous. See, first this is the your linked list. Again, previous is null. Of first node, start node, previous is null, and of the last node, next part is null. We are going to create a node. Okay. When we are going to insert the node at the end, we have to mark its next pointer as the null. here when we want to insert the node at the beginning, we are going to mark its previous pointer as null, while here we are going to insert it at the end. So we are going to mark its next pointer as the null. Now you have to take one PTR, okay, pointer variable. You have to traverse through this list until its next part is null. Once you receive this next part as null, you are going to mark its next PTR of next as new node, and new node of previous is equals to this PTR. Get it? See,
Yes,
move PTR. Here is your PTR, start and PTR. Move your PTR so that it points to the last node of the list. Add the new node after the node pointed by PTR. Okay. So here we will see algorithm. These 3 steps we are not going to see. New node of data is equals to value. Okay. New node of next is equals to null. New node of next is equals to null, that we did. Now repeat while set PTR is equals to start. Here your set PTR is equals to start, both will point to the same. Then now repeat step 8 while PTR of next is not equals to null. PTR of next is not null. Okay, then what we have to do? PTR is equals to PTR of next. So here it is your PTR. PTR of next is not null. So now P will point here. Then PTR of next is not null. So again PTR will point here. PTR of next is not null. Again it will come here. PTR of next is not null. Come here. Now PTR of null next is null. So what we have to do? It will now your PTR is pointing here. The pointer is here. So what we have to do after that? Set PTR of next is equals to new node. So set PTR of next is equals to new node. Okay. Then new node of previous is equals to PTR. New node of previous is equals to PTR. Get it? And exit. Simplest one. Understood?
yes, ma'am.
Okay, this is inserting node at the end of the doubly linked list. Then we will see here. This one algorithm we will see. After that remaining part you have to cover from your home. Okay, anyhow I'm going to post these PPTs on your Google Classroom. Okay. So inserting a node after a given node in the doubly linked list. After a given node in the linked list. Okay, so this much part is same. Set new node of data is equals to val. Now repeat step while PTR of data is not num, is not equals to num. Same conditions, just now we have seen this one. If this condition is true, then set PTR is equals to PTR of next, and then it will, we have seen it. This one. Okay, same. It will come until this part. Same example is there. After a given node, just assume that mistakenly दुसरीकडे draw केलं मी. Assume this is the list. Okay, 10, 20, 30 is there. And where we want to insert? After this node. Okay, after a given node. So this val is equals to, we'll consider val equals to 20. After this 20, I want to go. Now PTR is equals to start, same, assume this arrow the now. Okay, here is your start and your PTR is again pointing to this one. Now check. while PTR of data is not equals to null. PTR of data is equals to null, is equals to num whether condition is true or false. PTR of data is not equals to num.
True.
Condition is true, so it will do PTR is equals to PTR of next. So your P will point here. Okay, so assume this num as 20 and what we want to insert is 40. Val is equals to 40. Assume that one. Okay, PTR is equals to PTR of next. Now next is, again it will come here, PTR of data is not equals to null, is not equals to num. Condition true or false? Condition is false. So it will end the loop. Now set, this is the new node. Just assume that we have created the new node and 40 data is there. And now set new node of next is equals to PTR of next. PTR of next is equals to what? This 30. So this PTR of next, it will point here. Okay, then new node of previous is equals to PTR. This is the new node and its previous is equals to, it will point here. Now set PTR of next. PTR of next means this one is equals to new node. So it will point here, and then set PTR of next of previous. PTR of next was this and its previous is equals to new node, means it will point here. Get it?
Yes, ma'am.
Yes, ma'am.
Okay, in this way you can insert a node after a given node in the W-linked list. Okay, here it has been given pictorially. This is your list. So we want to insert this 9. Okay, allocate memory for the new node. Initialize its data part to 9. Now take a pointer PTR and make it point to the first node of the list. So start and PTR will point to the same node. Now move the PTR further until the data part of PTR is equals to value. So here your PTR will point to this one. Okay, after which the node has to be inserted. So we want to insert the node after 3 and before 4. So insert the new node between the PTR and the node succeeding it. Okay, so we are inserting here PTR next is equals to new node previous is equals to PTR of PTR, and then PTR of next of previous is equals to new node, and then new node of next is equals to PTR of next, we can say. So we can insert here the value. So this is the code. Now in the same way we can insert before a given node. You have to go through it and deleting from, again for deleting these 4 conditions are there. Delete the first node, delete the last node, simplest one, these 2, and then the node after a given node is deleted, the node before a given node is deleted. So I'm going to post all these PPTs in your in your classroom. Understood?
Yes, ma'am.
Okay. You can refer this presentation, and if you have any difficulty, you can ask me.